Good morning, everyone. It's really helpful for me, and I'm really happy to present our research as a climate resilient agriculture for Asia 18th TSAE International Conference. My name is Bunyad Allaberyanov, and we did research and we did research with our colleagues, and their name is Anwarbek Masharipov, Islam Kadirov, and Rahmatjan Ismailov, and the last one Atabek Mirzayev. We have conducted research on analysis and improvement of materials of the soil cultivating plowshare. As you know, the agriculture is a backbone of food security, and the efficiency of agricultural machinery plays a key role in sustainable farming. One of the most critical components of tillage machinery is the plowshare, which is the cutting elements that directly interact with soil. However, there are some drawbacks. As you know, plowshares often face challenges such as rapid wear, high energy consumption, and frequent replacement, which increase the cost of farmers and reduce overall efficiency. In the abstract, I give everything in a detail. What did we do together with our colleague? Especially in my country, I am telling about Uzbekistan. Uzbekistan is considered one of the hottest countries in Central Asia, and a large portion of its land consists of arid areas. Despite the challenges, our country has very favorable conditions for efficient use of land in agriculture. Every spring, as a cultivation season begins, our farmers engage in intensive soil preparation. They rely heavily on agricultural machinery to soften the soil, level it, and complete all sowing work. These machines are not just tools, they are the main working instruments of our farmers. For this reason, their continuous operability, long service life, and high productivity are crucial. They don't only contribute to the farmer's income, but also ease the burden of hard labor. The main goal of our study is to identify structural and mechanical properties of working part of soil cultivating plow, specifically the plowshare or Lemex, which is widely used in agricultural machinery in Uzbekistan. We also aim to apply the optimal heat treatment mode to improve its technical characteristics. Our focus is on enhancing and strengthening the mechanical properties of plowshare, ensuring that it becomes more durable, more reliable, and more effective in the field. In introduction, we firstly looked at the types of plows and their applications. For example, in autonomous plowing of annually cultivated lands or in the primary plowing of regional lands, it is recommended to use plow with turf cutting blade or angular cutter. For repeated plowing of already cultivated fields or for incorporating manure into the soil, a plow without turf cutter is more effective. In areas with dense roots, where breaking soil is difficult, clothes are simply overturned and left for other equipment to handle. On stony soils, plows are equipped with retainers to improve performance. Among these, Lemex type plows are particularly important. They are divided into two main categories: standard plows, which is widely used for annually cultivated lands, and the second one is a specialized plows, which is designed for bushland, swampy areas, gardens, vineyards, and even tired or flat plowing. This qualification helped us to better understand the role of plowshare material in different working conditions, which is focus of our study. In the material and the meta section, we used soil cultivating plowshares. As you know, in the screen there is a and the B and the AB and the ABCD different kind of pictures, which we use as a soil cultivating plowshare as a main materials for analysis. First, the plowshares were cleaned and prepared for testing, as shown in the pictures. For heat treatment, the samples were placed in the crucible with coal powder to create the required environment. After this, the treated samples were sectioned for further analysis. Next, we prepared the samples for microstructural examination. At room temperature, they were immersed in acid solution for a few seconds to remove oxide layer. then rinsed with water. To ensure accurate microscopic analysis, the samples were carefully microground and polished, giving us smooth surfaces suitable for metallographic observation. It allowed us to study structural changes and properties of the material after treatment. We carried out microstructural analysis of some materials at different magnification for both before and after. In this picture, in the result in discussion picture, especially we did some microstructural analysis of materials in different magnifications, both before and after heat treatment. Because as you know that when we give a heat treatment to the materials in the after heat treatment and the before treatment, structure of the materials will be changed because of heat treatment. First, we examined the result material at magnification from 5x up to 100x. This structure showed uneven grain distribution and weaker bonding, which explains its lower wear resistance. Next, we analyzed the Lemex material before heat treatment. Although it had better structure compared to the result, the grains were still relatively coarse and not fully uniform, which could reduce durability under heavy soil contact. After applying oil heat treatment, we observed noticeable changes in the structure at magnification of 5x, 10x, and 20x. The grains become thinner and more compact, showing improved hardness and wear resistance. In summary, I can see that the heat treatment significantly improved microstructure of Lemex material, leading to enhanced durability and mechanical performance. This suggests that treated plowshares will have longer service life and reduced wear agricultural use. In this section, we present microstructural changes and hardness measurements of the samples after heat treatment. On the left, you can see microstructures at high magnification. The images compare the result material, original Lemex, and the Lemex after oil treatment and the water treatment and the combined water oil treatment. After heat treatment, the grains become much finer and more compact, indicating improved mechanical properties. On the right, we have a weaker hardness test results. Before heat treatment, the Lemex hardness was around 175 HB. After quenching, hardness increased to 200 HB. With water quenching, it further improved to 220 HB, which is highest value recorded. For the combined water oil treatment, hardness was slightly lower at 195 HB. From these results, we can conclude that heat treatment significantly enhances hardness of Lemex, with water quenching showing the best performance. These improvements mean that the plowshare will have a better wear resistance, longer service life, and higher reliability when used in agricultural conditions. In this section, our hardness test showed that untreated plowshare had lowest hardness, around 447 HV, while water-treated samples reached about 602 HV. Especially if we consider safety factor, untreated plowshare was only 14.69, but with water quenching it increased to 20.16, the best result among all treatments, I think. In summary, I can see that water heat treatment proved most effective, giving plowshare higher hardness, durability, and reliability for agricultural use. In the next section, also we can explain a different kind of value. As you can see, bending moment, moment of inertia, bending stress, and safety factor. As you know, we should pay attention to the safety factor really carefully, because it can by this factor we know that we know how to improve. How to prolong life of the material. Bending stress was about 296 megapascal, while allowable stress was much higher, around 5,906 megapascal, giving a safety factor, as you know, 20.16. This means the material can safely withstand field loads. We also measured relative wear resistance, which was 2.408, and the wear rate was very low at 0.132. The general durability was calculated as about from 3.8 to 4 hectares, showing good working performance. Finally, plasma layer thickness was measured at 9 millimeters, which contributes to improved resistance and longer service life. In conclusion, as I told before, our study focused on improving the Lemix Plowshare to increase durability and reduce maintenance cost. Because if the cost of material increased really high, people are not able to buy this kind of material. And as you know, we should prolong the life of material. Design modification divided two Plowshare into three parts, which extended its service life by a factor of 3. The bending stress was calculated at about 293 megapascal, while the allowable stress was much higher, giving safety factor of 20.16. Wear resistance was improved, as you can see in our slides, and general durability of the blade reached up to 123 hectares, showing significant enhancement compared to the original design. Plasma hardening with 9 mm hardened layer further increases strength and resistance to wear. Overall, combination of the geometrically designed and the heat plasma treatment has made the Plowshare stronger, long-lasting, and more cost-effective for agricultural use. Thank you for your attention.